Now we're looking at rational functions, but just algebraically. So if we've been given the original equation, it's usually not factored already. We can take that and factor it. So I'm going to factor anything that can. The numerator, x squared minus 16, would factor to x plus 4 times x minus 4. The denominator, x squared minus 7x plus 12, we factor that as well. So that would factor to x minus 3, x minus 4. And now that it's in factored form, we can find the domain. So the domain restrictions are going to come from the denominator, and we just rewrite that into the domain. So if x minus 3 and x minus 4, we know that the denominator cannot equal 0. So that would be x minus 3 cannot be 0, which led us to x cannot be 3. X minus 4 cannot be 0, so x cannot be positive 4. And I just write that domain out into negative infinity up until we get to that first one, which is negative or positive 3, union, and then 3 to infinity, not infinity, 3 to 4, we have another asymptote, and then 4 to infinity. So this part we found the algebraically domain before, but we have not found wholes. So a whole happens when you have a common factor on top and bottom. So look for factors that do cancel. If there are factors in the denominator that do cancel, then you'll have the x coordinate of the whole at that location. We find the y value by substituting in the reduced function for x and complete the ordered pair. So what that's saying is I know that x minus 4 is canceling, it's a common factor, so the whole is happening at 4. But I don't know exactly what the y value is. So if I did that here, it would say we had x plus 4, x minus 4, over x minus 3 times x minus 4. These two things can reduce out to be just x plus 4 over x minus 3. So that told us that we're going to have a whole at x equals 4, and if I plug 4 in, I'll find the location. So that would be 4 plus 4 over 4 minus 3. 4 plus 4 is 8 over 4 minus 3 is 1. So our y value is just 8. That gives us a whole with the location 4, 8. Now the vertical asymptotes are still coming from the denominator, but it's the ones that are not canceled out. So look at the factors that do not cancel. Like we were left with an x minus 3. That's still going to be a vertical asymptote because we can't have 0 in the denominator. So x minus 3 can't be 0, which gave us x equals 3. So there's our vertical asymptote, x equals 3. The horizontal or slant asymptote takes a little bit of work, but we go back to the original part. So looking at the original, we want to focus on the degree of our function. If you look at the degree, you have 3 cases. So the first one is when the degrees are the same on top and bottom. So this one is degree n over degree n. You take the coefficients and put them over it and make a fraction. So in this one, in this one, it was the same degree over the same degree because it's degree 2. So I do the coefficients over the coefficient. In front of the x squared, we have a 1. In front of the bottom x squared, we have a 1 as well. So that's just going to say 1 over 1, which is just 1. There's our horizontal asymptote. Now, if the degree was smaller on top than and larger on bottom, it would automatically be y equals 0. If it was larger on top and smaller on the bottom, then there's no horizontal asymptote, but instead there's a slant asymptote, which we have to use long division to find. So an example of a degree small over degree large would be something like y equals x plus 8 over x squared minus 9. The first one's degree 1, the bottom is degree 2. So there's small over large. If you flip that, you could see large over small. All right, so the last thing is finding the y-intercepts and the x-intercepts. Those two things we still do algebraically. To find the y-intercept, we set x equal to 0 and we solve for y. So I could do 0 squared minus 16 over 0 squared minus 7 times 0 plus 12. We work it out, we're going to see we have negative 16 on top and 12 on bottom. And that would reduce. All right, so 0, negative 4/3 is the y-intercept. Our x-intercept, we set it equal to y and solve for x. So I think this is a little bit easier when we look at the factored form version. But let's say I set this function equal to 0. And really, we can just use the reduced version because the x minus 4s have canceled out. If I set this equal to 0, I'm going to have to multiply this up. And 0 times anything, let's put multiply here so you remember what we did. If I multiply that up, I'm still going to get 0. So I have x plus 4 equals 0. Solve that out, I get negative 4. There's our x-intercept. It's at negative 4, 0. We will really only need the numerator because when you multiply the denominator up, it's automatically going to still be 0. Okay, so let's look at a few examples of this whole process. We have a function x squared plus 9x plus 20 over x squared minus 4. We first want to factor it. So that would be x plus 4 times x plus 5. X squared minus 4 is x plus 2, x minus 2. So there are no common factors, which means I can't reduce that any further. That's an automatic no whole scenario. But the domain is going to be when the x's in the bottom make this 0. So we know the denominator cannot be 0, so that would say x cannot be negative 2 and x cannot be positive 2. We turn that into our domain and interval notation. So negative infinity all the way to negative 2, union negative 2 all the way to positive 2, union 2 to infinity. All right, our vertical asymptote is still coming from the denominator because I know that was where those excluded values came from. So those are actually our vertical asymptotes. The horizontal or our slant asymptote comes from the degree. So I have the same degree on top as I do on bottom. It's degree 2 over degree 2. So that would lead us to look at our coefficients. I don't normally write this out every single time, but to help us out as we are just learning it, this is how we can kind of think through the problem. Take our coefficient over our coefficients. That would be 1 over 1, which is just 1. So there's our horizontal asymptote, y equals 1. Our y-intercept we do by plugging in 0. So y equals, and you can use the factored version or the unfactored version. Either one is fine. So last time I used the unfactored, this time I'll use the factored. plug in 0 for x, and then we solve for y. So I have 0 plus 4 times 0 plus 5 over 0 plus 2 times 0 minus 2, and I get a negative 5 as my y-intercept. So 0, negative 5. The x-intercepts, if I solve, I'm setting this equal to 0. So x plus 4 times x plus 5 over x plus 2 times x minus 2. We multiply this up to the 0, and it just stays 0 equals x plus 4 times x plus 5. Using the zero product property, we find that x equals negative 4 and x equals negative 5. There are two x-intercepts. One's at negative 5, 0, and negative 4, 0. Okay, number 2. 2x squared minus x minus 6. The domain is coming from the denominator. So there's only one thing in the denominator, x plus 3. But we still want to factor it to see what we can get. So that top would be 2x times x to get a 2x squared. Factors of 6 would be 2 and 3. Let's see, and 2 here, 3 there. So the outside is going to give me a 4. The inside would give me a 3. I need a negative 4 plus 3x to get a negative x. So that's what that would factor to, and I don't have anything that's canceling out. So there's no holes in this scenario. But the denominator would be 0 when x is equal to negative 3. So I can go ahead and find the domain. Negative infinity all the way to negative 3, union negative 3 all the way to infinity. And that's just coming from x cannot be negative 3, or it would make the denominator equal to 0. It did find the actual vertical asymptote. So that x plus 3 in the denominator is our vertical asymptote. So x equals negative 3 is the equation. Our horizontal asymptote is coming from the degrees of the original. So this is degree 2 over degree 1. So that means it's larger on top and smaller on bottom. That was the case that we said there was no horizontal asymptote. There will be a slant asymptote, but we're not finding that yet. The y-intercept, we plug in 0 for y. I get y equals, 0 for x. 2 times 0 squared minus 0 minus 6 over 0 plus 3. You'll see it's kind of easier in standard form, but you end up with negative 6 over 3, which is just negative 2. So 0, negative 2 is my y-intercept. And the x-intercept is actually easier if we looked at the factored form. So I set y equal to 0 and we solve for x. But again, I'm going to be multiplying the denominator up here. And that's automatically still 0. So 2x plus 3 times x minus 2 equals 0. We use the zero product property. That would be 2x plus 3 equals 0. X minus 2 equals 0. We solve it out. I'm going to get negative 3 halves and positive 2. So those are our two x-intercepts, negative 3 halves, 0, and 2, 0. So go ahead and try number 3 on your own. Just pause the video and see what you get. Okay, so if you've already done this one, there's nothing to factor on top. That's okay. So we leave that one the way it is. You could factor out a negative 1 if you want, but it's really not going to do much yet. I can factor the denominator to be x plus 9 times x plus 1. For something to cancel out, it had to be the exact factor. So while that says x plus 9 and x plus 9, that's not exactly an x plus 9, because that 2 and that x is a 2x. All right, so now if I look at the denominator, x cannot be negative 9 and x cannot be negative 1. That would leave a domain with negative infinity all the way to negative 9, union, negative 9 all the way to negative 1, union, negative 1 to infinity. One of the things I've seen students make a mistake of is just mixing up the order that these come in. So our domain should always go left to right. So negative 9 is going to come before we get to negative 1. So you don't want to do that out of order. Holes come from if there was a common value. This has no hole here. Our vertical asymptote is coming from the denominator. We saw these two right here, so x equals negative 9 is one, and x equals negative 1 is the other. Our horizontal asymptote is based off the degree, so we have a degree 1 on top. It's just x to the first, and a degree 2 on bottom. So this is where it's a small over large. That's automatically going to be y equals 0. All right, and then our y-intercept, if I plug in 0 for my x's, we end up getting 9 over 9. Which is just 1, so it would be 0, 1 for my y-intercept. The x-intercept, if I set this up equal to 0, the denominator multiplies up to 0, which is still 0, because anything times 0 is 0, but it's equal to negative 2x plus 9. So we solve that out. I get negative 9 equals negative 2x, and x equals positive 9 halves, or 4.5. So 9 halves, 0 is my only x-intercept. There are a few of these in the lab manual for you to practice with.